Welcome back to the lecture series of network theory. Today I will discuss about the application of another important theorem in network theory, which is Norton's theorem. And like Thevenin's theorem, I will also cover this theorem in three classes. The first class again will be based on DC circuits and independent sources. The second class will be based on DC circuits and dependent sources. And the third class will be based on AC circuits. So let's start the first class on Norton's theorem. The Norton theorem states that any two-terminal active linear bilateral DC network consisting of independent energy sources can be replaced by an equivalent circuit consisting of a current source and a resistor connected in parallel, where this current source is represented by I suffix n, where this n stands for Norton's. Now this IN is the short-circuited current through that concerned or output terminals after removal of that load resistor or concerned resistor if there is any. And the resistor is represented by R suffix n, where this Rn is the equivalent or internal resistance of the network when looking from the concerned or output terminals with all energy sources deactivated and replaced by their internal resistances. Now what we understand by deactivation of energy sources, whether it is voltage or current source, that I have discussed in my previous lectures. If the voltage source is an ideal voltage source, we know that we simply short that path, and if the current source is an ideal current source, then we simply open that path. Now in this circuit we can see here we have multiple resistors and we have an independent voltage source and an independent current source. Now suppose this RL is our concerned or output resistor which is connected between these two terminals A and B. Now as per Norton's theorem, this whole circuit other than this resistor RL can be represented by a single current source which is called the Norton's equivalent current, and also a resistor which is the internal or equivalent resistance of the whole network other than this load resistor, and these two IN or RN will be connected in parallel. This is our equivalent circuit. So this is our A terminal and this is our B terminal. Now what we have on the left side of this AB terminals, the whole circuit can be represented or is represented here by this single current source which is called Norton's equivalent current and represented by IN, and a single resistor which is called Norton's equivalent resistance, and they are connected in parallel. Now if we want to find out the current value, suppose if the current value is I through this resistor, then what we have to do after obtaining this Norton's equivalent circuit, we have to connect back this load resistor. So when we will connect that load resistor with this Norton's equivalent circuit, so this will form a closed path and easily we can find out the current which flows through this load resistor RL. So for doing that we have to apply the current division rule. So I will be the opposite resistance which is the Norton's equivalent resistance Rn divided by the summation of both the resistance values, so Rn plus RL multiplied by the main current which is the current of that Norton's equivalent current source. So here it is IN. So this way we can find out the current value or the voltage drop across the concerned or load resistor by applying Norton's theorem. Now we will see that how we can Nortonize a DC network having independent sources in multiple steps. So here we have taken the same circuit that we have seen in the previous slide. Now what we do here, in the first step we remove the load or concerned resistor. So this RL is the load resistor which is connected between these two terminals A and B. Now after that, after removing this load resistor, we simply short that path between those two terminals. So this is our A and B terminals, and after removing this load resistor we have shorted that path, and we have kept all other components in the circuit as they were in the original circuit or network. Now after removing the concerned resistor and after shorting that path, we will next find out the short circuit current which flows through that shorted or short circuited path. So suppose that current value is ISC. So our next task will be to find out this value, and for doing that we will apply the conventional network analysis methods whatever will be suitable for this circuit, like KVL, KCL, voltage division rule, current division rule, etc. Now after finding out this short circuited current, what we will do is we will deactivate all the energy sources from that circuit. Now the rule of deactivation we already know. So in this circuit, since we have an ideal voltage source here, so we will simply short that path, and in the original circuit we have here a current source, so we will simply open that path between, or open those two terminals between which the current source is connected. So after removing or deactivating the energy sources, the circuit will look like this. Now we will look from the concerned terminals towards the circuit. So since this is our concerned terminals between which the load resistor was connected, so we will look at the circuit from this side, and we will find out the internal resistance of the whole network. So since we are looking from this side and we want to find out the equivalent resistance of this network, so we will start our simplification from the opposite side, means from this side. And as per this network, as this path is a discontinuous path, so here we will not consider R3, rather this R1 and R2 are connected in series. So first we will find out the equivalent resistance of this path, series path, and then with that equivalent resistance this R4 will be connected in parallel. So accordingly, by applying the formula of equivalent resistance of a parallel path, we will find out the equivalent resistance, and that will be the internal resistance or equivalent resistance of the whole network with respect to these two terminals when we are looking from this side. Now that equivalent resistance will be called as Rn, and after obtaining this ISC and Rn, what we will do, we will connect this ISC, that current source having value ISC, and this equivalent resistance Rn in parallel. So in this circuit, this will be our In and this will be our Rn. And after connecting these two components, we will connect back the load resistor that we disconnected at step 1. And this will be our modified simplified circuit as per Norton's theorem. So now if we want to find out the current value which flows through this load resistor, that will be, again, I will be equal to Rn divided by Rn plus Rl multiplied by the value of the current of that current source, In. So this is the way how we can Nortonize a DC network having independent sources. Next we will solve a few numericals by applying Norton's theorem. Now in this network, as you can see here, we have multiple resistors and we have two current sources. Now in this network we have to find out the current value which flows through 3 ohm resistor. So this 3 ohm resistor is our concerned resistor. So we will mark these two terminals, and then in the next step we will remove this concerned resistor and we will simply short that path between those two terminals AB. So after removing that load resistor and after shorting this path, the circuit or modified circuit will look like this. Now our next task is to find out the current value which flows through this shorted path. Now in this modified circuit, what we can see here, that we have two current sources and we have simply two resistors and this shorted path. So we, by applying any conventional method which will give us a faster result, that we can apply. So here I have chosen to apply superposition theorem to find out the short circuited current. Now if we first deactivate this current source and we only consider this current source, then the circuit will look like this, as if we have one current source having value 4 ampere, and with that we will have this 4 ohm 2 ohm resistor which is connected in parallel, and then we will have this 2 ohm resistor and then this shorted path. So this will be our circuit when we are not considering this current source, and this resistor also have value 2 ohm. Now we have to find out what is the current that is flowing through this between these two terminals. So let's assume that value as ISC1. So here, as we can see in this simple circuit, we have 2 ohm resistances which are connected in parallel, and we have only one current source. And since both the resistances are having the same value, so here when we will apply current division rule, the current which will flow through this 2 ohm resistor will be half of the main current value. So even without applying the formula of current division rule, we can find out. So here the ISC1 will be just half of the main current value, which is 4 ampere. So it will be 2 ampere, and which will flow downwards. But if both the resistances are not having the same value, then we have to apply the formula of current division rule. Now in the next step, if we consider this 10 ampere current source, and if we deactivate this 4 ampere current source, then the modified circuit will look like this resistor, then we will have this shorted path, and here we will have the current source having value 10 ampere. Both the resistances are having value 2 ohm, and let's say that current which flows through this shorted path between these two terminals AB, that current value is, say, ISC2. Now interestingly, we can here see that when this current value of this current source will flow this way in this direction, and when at this point that current will come here, it will get two paths to flow, one shorted path here and one path that has two resistances connected in series. Now since this path has zero resistance, so the whole current will flow through this path only, and no current will flow through this branch or path. And we can also prove by using the current division rule here. That means through this path, the current which will flow, that will be the whole 10 ampere current. And since the assumption of the direction of this current ISC2 was downward, and as per the direction of this 10 ampere current, the current which will flow through this shorted path, it will be upward. That means as per our assumption, the current value will be negative, so it will be minus 10 ampere. That means if we apply the concept of superposition theorem, the short circuited current through this path will be algebraic sum of these two currents because of those two current sources. So it will be ISC1 plus ISC2. ISC1 has value 2 ampere and ISC2 has value minus 10 ampere. So it will be finally minus 8 ampere, and the direction of current will be downward. So with respect to that direction, the current value is minus 8 ampere. That means actually current is flowing upward through this shorted path. Now our next task is to find out the Norton's equivalent resistance for the whole network. Now for doing that, we will be deactivating the energy sources. Now in this network, since we have both the current sources, so we have simply opened those two paths. So between these two terminals, this current source was connected, so we have simply opened those two terminals, and here also we have applied the same rule. And this shorted path between these two terminals, originally this resistor was connected, that we have already removed in step 1. So other than this resistance in this network, we have only these two resistances, and we will be looking from this side. Now the equivalent or internal resistance of the whole network other than this concerned resistor, when we will be looking from this side, it will be with respect to these two terminals. Now we will start simplifying this network from this side. So with respect to these two terminals, if we want to find out the equivalent resistance, then we can see here that this resistor and this resistor, with respect to or between these two terminals, they are connected in series. So the equivalent resistance, which is Norton's equivalent resistance, that will be simply 2 plus 2 means 4 ohm. That means the final circuit will have this IN, which has value minus 8 ampere. With that, we will have one resistor which has value 4 ohm, and with that we will have another resistor which is the load resistor that will connect back here in the final step, and that load resistor has value 3 ohm. And our main objective was to find out the current value which flows through this load resistor. So I will be simply here 4 divided by 4 plus 3 multiplied by 8, or we can say minus 8. So it will be finally minus 4.571 ampere, and this 4.57 ampere current flows through this 3 ohm resistor in downward direction, and that value is negative. So as per our assumption, the current flows downward and that value is negative. That means actually the current is flowing upward through that load resistor, and that value is positive. Next, we will simplify another DC network having independent sources by applying Norton's theorem. Now in this network, as you can see here, we have multiple resistors again, and we have one independent voltage source and one independent current source. Now we have to find out the voltage drop across 1.5 ohm resistor, that means this resistor. So this is our concerned load resistor, and let's mark these two terminals as A, B. So in the first step, we will remove this load resistor and we will short that path between these two terminals AB. So if we do that, the circuit will look like this. So this will be our circuit of the next step, where we will find out the short circuited current of this shorted path between AB terminals. Now for doing that, we can apply any method which is convenient or which can give us this value. Here we can apply again superposition theorem, or else we can apply any other suitable method. Now this time I have chosen to apply KCL, which can give us the value of ISC faster. So here, as we can see, we have 1, 2, 3 and 4 parallel branches, and we have two principal nodes here. So if I choose this node as our reference node, so potential of this node will be 0 volt, and let's assume potential of this node as V. So here we will apply KCL at that node, and we will form the equation. So here the algebraic sum of all the incoming currents with respect to this node will be equal to algebraic sum of all the outgoing currents. So here for this current source, the direction of current is given, and for this source also we have, for this branch also we have assumed the direction of current, and that is downward, or with respect to this node the current is leaving. For other two branches, the current directions are not given, so we'll again assume that the currents are leaving with respect to this node. So here the only incoming current is 4 ampere, so it will be 4, and that will be equal to algebraic sum of all the outgoing currents. So here the current which flows through this branch will be the potential difference will be V minus 0 divided by the resistance of that path, which is 4, plus the current which flows through this path, and that is again V minus 0 divided by 4, and current through this path. and that is V minus the voltage of this source, and since this positive terminal of this voltage source is here, so this voltage will be subtracted, voltage value. So V minus 6 divided by the resistance value, that is 1. So if we simplify this equation, then it will be V plus V plus 4V minus 24 divided by 4. So if we simplify further, then it will be 6V, that will be equal to simply 40, or we can say V will be equal to 40 by 6, so it will be 20 by 3 volt. Now our main objective of this step was to find out the short circuited current through this path. So ISC will be, it will be V minus 0 divided by 4. So it will be 20 by 3 minus 0 divided by 4. So it will be 20 divided by 12. That means it will be 5 by 3 ampere. Now in the next step, we will find out the internal or equivalent resistance of the network. And for doing that, we will deactivate all the energy sources from the circuit. So here, as we can see in the original circuit, we had a voltage source here, and that was ideal in nature. So we have simply shorted that path, and where we had one ideal current source, so we have simply opened that path. So other than these energy sources, we had three resistors, and when with this open terminals AB, when we will be looking at this circuit, we will be seeing this type of circuit. And with respect to these two terminals AB, we have to find out Rn, or internal resistance of the network. So we will start simplifying this network from this side. Now with respect to these two terminals, if we want to find out the equivalent resistance of this network, and if we start simplifying from this side, we can see here that these two resistors are connected in parallel. So the equivalent resistance of that path will be simply 1 multiplied by 4, 1 plus 4, that means it will be 4 by 5 ohm. And with that equivalent resistance having value 4 by 5 ohm, this 4 ohm resistor will be connected in series. So the equivalent resistance, which will be finally called as Rn, that will be 4 by 5 plus 4. So it will be simply 24 by 5 ohm. So by now we have already obtained the short circuited current ISC, which is 5 by 3 ampere, and equivalent resistance or internal resistance of the network, which has a value of 24 by 5 ohm. Now in the last step, we will draw the modified circuit where we will have the one current source having value 5 by 3 ampere and one resistor having resistance value 24 by 5 ohm. And with that, we will connect back the load resistor or concern resistor, which for this network has value 1.3 or 3 by 2 ohm. And we wanted to find out the voltage drop across this resistor. So here, suppose if we want to find out the current value, then it will be simply the opposite resistance 24 by 5 divided by 24 by 5 plus 3 by 2 multiplied by the main current, which is 5 by 3 ampere. So if we simplify further, then it will be finally give us a value which will be 1.27 ampere. So this is how we can apply Norton's theorem in a DC network that has only independent sources, and we can obtain the desired parameter. Now here we have so far obtained the current value, and we wanted to find out the voltage drop across that 1.5 ohm resistor. So it will be simply 1.27 into 1.5, so 1.91 volt. With this, I end today's class. Thank you.